All right, let's begin for the day, I suppose. Just take a drink of water. Maybe today will be a relatively short lecture, or an easy one. I think I'll start with a data structure called tries, and then maybe I'll do a little bit on graphs. And that's how I think it's going to go. So, put the live chat back, so that's good. Okay, so I did grade some of the 341 exams last night. I'm not quite done. So, as I said, I promised 341 exams done today, and so my promise is not yet fulfilled, but I did work on it. So today I'd like to cover, and so I guess, is there anything about the project that we should talk about? Any questions about the project? Anything like that? So there was, okay, I think I'll just begin, and then if you have anything else to say, I will talk about it. Okay, so what is a trie? Or that's generally how you spell it. So it's a data structure that we can use to basically to remember, or what should we say about it? It's a data structure we can use to I think the application do a bit of autocomplete, if you know what I mean. So I'll explain what I mean by that. That's kind of the application. It stores, for instance, like if you store a string, you split the string into letters, and each node is a single letter. And so let me show you an example of how this is going to work. So for instance here, let's say that here's our root, and our root is going to be nothing. So it's going to be like empty. And I'll show you why the root is empty in just a second. But then let's add the word hat, okay? So the first thing you're going to do is you're going to add a node for the letter H, and then you're going to add a node for the letter A, that's a child, and then you're going to add a node for the letter, oops, maybe I should just make these copies. And you're going to make a node for the letter T, and then you'll connect all of these. So let's do that. And that's to make it seem a little bit better. So now we can connect this node with this node, and this node with this node. And so now what we do is we have hat in our trie. So you generally have to add something to this node here to indicate that it's the end. So to indicate it's the end, I'm going to put a little star on it. Sometimes you can put a little count if you want to count the number of times that word has occurred. So what you know here is that H is a letter in a word, but it's not the end of a word. A is the letter in a word, but it's not the end. And T is a letter in a word, and it is the end of a word. And so now let's insert the word maybe has, right? And so in this case, what you're going to do is instead of making a whole new tree or a whole new branch, what you're going to do is you're going to basically copy this thing, change this letter to S, and then you're going to do this, like that. And so now you have the word hat and has inside of this tree. So now if you have the word, say, R, right, you need to create a whole new path because the first letter isn't H, it's A. So actually, let me just copy the A node. There we go. And then we can make a little path for R and a path for E. R, and then E gets a star. So this is generally how a trie structure works. Basically, there are some ways that you can contract them, there's some ways that you can optimize, but this is like the basic idea of a trie structure. And you see how you can kind of use it for autocomplete. And you see why I'm saying autocomplete is one of the ways to do it, is because if a user types in HA, you can do a little search of this tree. You can do kind of a traversal of the tree, or you can do some kind of, maybe not a full traversal, but you can go down a few levels to see what the most common words are. So maybe instead of stars, you have counts, and you can maintain, for instance, like, oh, this is, when someone types in HA, they generally will mean has first, and then maybe they mean hat, and then maybe they mean happy, right? So if they mean happy, then of course we need oh, and let's add in the word hats, right? So the word hats is going to be something like this. I don't know why it's grouped all that together. I don't like that. There we go. And give me the S star. So we notice here that there we are. And then maybe we'll add the word happy as well. So let's, we're doing a bunch of H words. And let's put a P here. I'm going to have to kind of squish them together. So, let's change this to a P. And then and you see that this isn't really any of the other data structures that we've seen before, right? This thing is kind of a different sort of animal, because you notice that each node itself is not really conveying a whole piece of information, right? Each node is actually just conveying, unless it's just, I guess you could always say, well, A is a word, so you could put a star on A, but we haven't inserted the letter A as a word yet. But if we did, then A would get a star. And so what you would see is that maybe A is a word, and then AR, but AR is not a word, but then ARE is a word. So that's why this one has a star, and this one has a star, and this one does not have a star, right? And then, of course, if we connect all these, we can make happy work out. So here's happy. Like that. Well, so you notice that a node can have 5 million children, or is there a limit? Well, there is a limit, right? How many children can a node have? The answer is generally going to be about 26, right? Maybe if you include hyphens, so maybe 27. If you include, you probably won't include commas or spaces or tabs or anything like that, and you'll probably smush all the letters down to lowercase. So it's not going to be 52 children, it'll probably be 26 children. But this is basically, this is one way how, how you can make a very quick and dirty, cheap and easy autocomplete feature, right? Because, yeah, so it's not 2 or 3. Yeah, so the thing is that you're thinking about the node structure. So if we look at the individual node, right, what is the node going to have? So let's blow up a node, right? It's going to have, letter equals P, right? And it's also going to have, star is equal to some Boolean. In this case, it's going to be false. I guess I'm using the Python notation for false. Let me use the C++ notation. And then it's going to have like a vector of children, right? Right, so that's what each node is going to look like on the inside, right? And we can even, my secret here is I'm going to implement this in Python because I don't want to actually implement this in C++ if I can avoid it. Just because I'm going to show you, I'll show you why it's a little bit easier in Python. The secret is that actually I'm going to use a dictionary instead of a vector here. So my secret is that I'm going to use a dictionary, which is really a hash table, right? So this is an application of hash tables where you can even use a bit of a hash table here. And the good news is your hash tables can even be like, well, anyway, so let's not even think about that yet, but I'm just going to use some dictionaries to do this. And so the reason why I want to do this is mainly because I think that if I implemented it in C++, it would take me like 4 times the length of time. And Python has a lot of nice built-in features that will allow me to do this a little bit easier. So Python has features that will make this this very fast rather than very slow, right? Because if I would have to either implement my own hash table or I'd have to do something with my own vectors of children or something like that. And, in all of those cases, and plus the string manipulation in Python is way easier than the string manipulation in C++. Really what we need to do, what needs to be done is we need to just write an STL library that does all the Python string manipulations in C++, and then C++ will be perfect, right? C++ is a great language. It just doesn't have all of the nice string manipulation functions that Python does. It's going to be just slightly harder at every stage to do this process. The other thing I'll show you is how you can make data structures in Python to some degree. So maybe that's interesting to you, I don't know. Because remember, Python doesn't have pointers. It has references but no pointers, so we're going to have to do things slightly differently. All right, so are you ready to implement this structure? And then maybe we'll talk about some optimizations. So does everyone basically understand the structure of this thing? Like, I think I've made it pretty clear. I think it's actually not that hard of a structure to understand. It's just something that you would not necessarily think of. I was actually solving a problem, and I believed that I had invented this thing, right? And I believed that for about a month until I bothered to actually look it up, and then I realized that obviously I had not invented this thing. This thing had existed for 20, 30, 40 years before I had even, thought of it. So, but the point is that I was like, wow, this would be a really cool way to store words and do some kind of autocomplete feature. That's actually what I was doing with it. And I, of course, in my stupidity, I thought that I had invented the thing, It's like someone draws a circle and thinks they've invented the wheel, right? So, so let's implement this thing. So let's do maybe let's do something in data structures. Let's call this the try. And let's basically close all this other garbage. And then, of course, I want to before people complain, in 201, but by this point, people will have already complained like 800 times, about the font size. They'll be like, it's too small, I can't read, I don't know what's going on, blah, blah, blah. I'm like, shh, it's okay. I got you. So, all right. Okay, so you remember if name equals main. So let's make our node class. So this is just like in C++. We're going to make the node class. I don't know if you've taken the version of Python where I've included classes now. Most students hate it. They absolutely hate it. They can't tolerate it. They hate everything about classes. But anyway, here we go. So instead of doing, this is the class constructor here. It's a method called underscore init, like this. And notice in a class, the first argument is always self in all of the functions. So remember in C++ you have this, in Python you have self. And Python is good and bad, right? It forces you to pass self explicitly. So the secret is that whenever you call, let's not even do that. So what things does the node need? The node needs self.star equals, let's say, letter. Star equals false, right? So that's just a default parameter. And what else? And so nothing. So, and then we'll do self.children equals dictionary, empty dictionary, self.letter equals letter, self.star equals star. And so that's actually one nice thing that Python does, is it allows you to have the variables inside the constructor be the exact same except for with self. So the self.variables are variables that exist within the class. The letter variable and the star variable are the local variables from the constructor right here. So basically what this is going to do is this is going to allow us to build nodes. And that's really all we need in the node class, I think, right? I mean, we could do a self.count. And I know I'm doing star and count, but whatever. Count should be 0. Count should be 0. Okay. So now we're going to make another class. So let's make a new constructor. The new constructor is basically going to say self.root is going to be equal to a node. The node is going to have a null letter. It's going to be an empty string. And then it's not going to be starred, right? So it's going to be false. We can just leave that blank. So basically, this is the same as doing like this root, this count, this children, etc. Right? That's what this is the equivalent of doing in C++. But in Python, it's just all called self. Okay. So let's make another method. Let's say def insert word. Right? Let's insert a word. And you remember what pass does. Pass is a no operation. So I'm just inserting it. The reason why I insert pass into these is because it's basically like, in C++, it's basically like doing this, right, after a function, just putting in some empty brackets. And the reason why I do that is because if you don't put it in, then it's looking for something at the next tab level. So if I do, say, what's the next thing going to be? Like find word or something like that. What it's, and you see I put pass in there. You see that there's all this red. It's basically like indent expected, indent expected. It it doesn't know what it's looking for. So that's why you put passes in. You put passes in to hold the indent level so that you can kind of go on and create other things and it won't have any errors. So what else should we do with a try? Yeah, maybe def autocomplete. Partial, right? So maybe that's the stuff we want to do here. Maybe this is what we want. Okay? So let's see what we can do, right? So what we're going to do is, for letter in word, and we're going to set the current node to self.root. And then what we're going to do is we're going to say, if letter is in current.children, right? Then we're going to say current equals current.children letter. And then, else, we're going to add it. So we're going to say current.children equals, letter. And remember, this is a dictionary. So I'm adding it under its letter. It's going to be a node. I guess I'm storing the letter twice. And, you know, if it's, we'll determine if it has to be start at the end, right? At the end, we're going to do a current dot star equals true and a current dot count plus equals 1. Okay? So that's what we're going to do. All right. And maybe we'll have some kind of print for it. So you see how you can kind of do a tree structure in Python here. You see, basically you have to forget all about the arrows versus the dots. Everything just becomes dots because there's no such thing as a pointer. But everything is a reference. So basically what we're allowed to do here is we say current.children. This would normally be current arrow children, but now it's just current.children is equal to the node letter, right? And so I think this is basically the insert function, right? This basically inserts the word. And so now let's say we're going to find a word. So we're going to do the same thing, right? So if the letter is not in the current.children, we're just going to return false. And at the very end, if current.star, right? See, I did it. There we go. And so now if current.star, so that means if it's actually a word, right? We can return true. Actually, why don't we return current.count? Because if it's a word, its count is going to be bigger than 0. If it's not, then it will just be 0. So we can just return current.count. Okay, so that's probably the safest way to do it. Okay. And so you see here that this is actually a pretty simple structure, right? Okay. Let's see what I want to do here. So for autocomplete, what do we want to do? That's a hard question, right? Like, you might only want to traverse a certain number of things. You might want to do that. Like, let's do a full traversal currently. Right? Let's do a full traversal of the subtree. And the reason why is because I'll just show you everything that's under there rather than just some of the things. In a real autocomplete, right, like if you're doing it on your cell phone or something, they're going to limit the number of results to 5, so they're just going to pick the most 5 common things and just show you those. They're not going to be doing a search through the entire dictionary of words to look for all the words that might, that might have some kind of thing in them. So, okay. So let's return, I have an idea. We'll return a list of words, which are partial matches. Okay? Or which are matches to the partial string. So it's not a full autocomplete in the sense that, and maybe we can make this function recursive. So we'll have a partial, we'll have a current, and then we'll have, say, a list, and we'll have the results. Okay? And so this is one cool thing about how Python works. We can create a results function like this, or a results list, and then we can call autocomplete help. Oh, how do you call a method? You call a method by doing self dot, same thing as getting a parameter. So let's do the whole partial thing. Self.root results. So remember that it passes lists by, this thing will pass lists by reference. So Python passes lists by reference. So that means that every single what should I say? Every single what am I saying? Yeah, every single word that gets appended to this list is going to get appended at any part of the recursion. So let me show you what I mean by that. So let's say if partial, so if partial is not an empty string, what we're going to do is we're going to say current is equal to current dot. Actually, I guess we can do it up here, and we don't need the partial here. So, yeah, 4 letter in string. Actually, let's do while partial, and then I can show you a different way to do it. So I'm going to do current is equal to current dot children letter like this, and then at the end we're going to do, I guess current should be self.root. And then what we're going to do here is we're going to say current, and of course we need to check if letter in current.children, else return empty list. So the reason why I'm returning an empty list here is because if there's no words, if you type in a string of gibberish and there's literally no words that start with that, then we're just going to return an empty string. There's no matches. And then here I'm going to say partial is equal to partial, and then I'm going to slice from 1 till the end. So remember what this does. This is a slice that takes the first element, or I should say the element partial 1, partial 2, all the way down to partial length of partial -1, and it just basically it slices off the first letter. So this is a different way of doing it. This is actually probably a way worse way of doing it. I just wanted to show you a different way of doing it. It's definitely less efficient in terms of the string operations, but Python gives us so many really good string operations. Like look at, like here we have all this nice for looping that we can do with 4-letter in word, and all of this dictionary functionality. It really makes all of this code kind of elegant, if I'm allowed to say that. So then here, what we're going to do is once we get to the end of the partial, we're just going to pass current. And so what we're going to do is we're going to say, inside here, we're just going to say for, there is no such thing as partial. So if current, or no, not if current. We're going to say for child in current.children, and let's say child letter, right? Because that's actually this is a dictionary, so it's returning the letter. We are going to oh, I think I know why I wanted to do it recursively. So let's save original partial like this. And I'll show you what I'm doing here in just a second. So what we're going to do is we're going to say, okay, if current.children at the child letter dot star, then what we're going to do is we're going to add the partial plus child letter, and that's what we're going to append to the list. We're going to append this string. But either way, what we're also going to do is we're also going to do autocomplete help on partial plus the child letter. So this is where we're going to recurse current.children child letter results. So I'm passing in the results, and then we'll do self dot. And so I think this should do it, right? Because this is taking every letter that's in the current.children. If the thing has a star on it, then we're appending the entire partial plus that letter, so that's appending the entire word. And then what we're doing is we are recursing, where we have a new partial, which is that much plus some, and we're starting there, and that's the result. So I think what we want to do is that. And then we just want to return results. Okay, and I'll talk about what I'm going to do with repr in just a second. Repr is an overloaded method. So repr is actually an operator overload in Python. And basically it overloads the string cast. There's also essentially what I wanted to do is whenever I print out a tree, I wanted to just print. So it has to return a string. So currently let's return nothing. But okay, so let's write some code that actually uses this and test this out. Right, so okay, try. There we go. So let's do s is equal to input, enter command, while s is not s dot strip dot lower not equal to quit. What we'll do is we will do s dot split, and so we'll say command word. And so if command, let's actually hit all of this with dot lower before we do a split on it. Well, first let's do if that's just a little safety check to prevent us from crashing. So if the command is going to be add, then we will call my try dot add or insert word, and we'll insert the word. Elif the command is equal to complete. Then what we'll do is we'll call my try dot autocomplete on the word, which is going to be the partial, and we'll print out the result. And then finally, let's do something else. What other operation do we have? Find. So okay, so I think that should be good, right? And then, of course, what we want to do is we want to print out my try, but of course this is actually going to print out nothing initially. I'll have to implement this. And then to prevent an infinite loop, which I don't always do, let's input this again. Okay. So, you see that this was moderately fast in Python. It would have taken me a lot longer to do this in C++. Let's see, Shadow's name from outer scope, I don't really care. Okay. Okay. Let's run it and test it and see what happens. Okay, I think I gotta do this. Enter command. Let's add hat. Hat has been inserted. Add has. Okay. Okay, and now let's complete ha, right? This will be our first test to see if it gives us a list that has hat, has, and happy. It does not. It does not. So maybe we do need to see what's going on in the tree, so let's quit. Let's write this method here so we can actually see what's going on. Okay, so what we're going to do here is for every child letter in current.children, we are going to add, we're going to do a display on current.children child letter. Well, let's say let's see, current.star. We can take total string plus equals star, and then we're going to do total string plus equals end line. Okay. And then we'll do total string plus equals this. I think that should do it. And of course, this needs a self.display. And then we need to return the total string. So this should hopefully display the tree. If it doesn't, then I'm wrong. Okay, let's see what else happens. So that's not right, right? Because the root got starred instead of the T. We want the T to get starred. Oh, yes. That's the whole point. There we go. That doesn't seem right. Because it should be... Oh, that doesn't seem right either, does it? Because these need to be at the same level, and they're not at the same level. So it's possible that this tree structure is just wrong. So let's go back and look at our insert and see what I've done wrong there. So current is equal to self.root. I agree. Yes. If the letter is in the thing... Ah ha 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 ha! This will fix it. Don't worry, I will fix it. There we go. So if it's not in there, we need to add it, but then I wasn't going down to the next current level, so that was a problem. Okay, let's try again. There we go. Perfect. See that? So the root is right here. It's a blank. Well, okay, let's actually make the root, say root on it. That way we can see it. And then let's add hat. Ah, perfect. So you see that here H has a child A has two children. It has S and T. Both have stars. Right, here is HAPPY, right? So Y gets a star, T gets a star, S gets a star. Okay, so now let's test another command. Let's try to complete ha, right? Wonderful. See? What it did was it says has, hat, and happy. It goes and it scans down through the tree, right? It says H, do you have a star? No, you don't. A, do you have a star? No, you don't. A, S, do you have a star? Yes, you do, right? And then T has one. And so both of those get appended. And then happy gets appended because it goes down this child, and finally Y star. Cool. What else should we append? Let's append, so let's add a new word. The word word. Right? You see that this structure, and then let's add worry. Wart. Add worm. Nope, that's not what I want. I guess WOM is now a word. Oops. I don't have a delete, so we're stuck with that. Let's add worm. And then let's add words. So you see here that in this autocomplete, it's going to be WOR, and then of course here's the crap WOM star, which is, not correct. So if we wanted to implement a delete in this thing, the thing that you have to remember is if you're going to remove a word, what do you have to do? So you can't just delete this node. So for instance, if I say remove the word word, right? But words is still a word, and like worry is still a word. So if I were going to remove these things, I can't just delete this whole path. In fact, I can't even delete this node here. Like if I add, for instance, like wordsmith, right? So you see that here, if I tried to delete the D, I would be ending up deleting all of these things. So if I want to delete a word and it has a star, then I just delete it. And if it has no children, then I can take the node out. But if it has any children, I have to kind of leave it in this tree, right? So whoops. So if I complete WOR, what I get is word, words, wordsmith, worry, wart, and worm, right? So yeah, I kind of like this data structure too. It's not something that is like taught very often, but it's also not something that's insanely complicated or something that's, it's just something that if you hadn't really thought about it, you might be like, oh, I would never have thought to do that. And so I kind of like it, So there is one optimization that you can do. So notice here how we have a P and a P and a Y. But the point is that here we don't have any, there's no other things that pop off currently. So one way to optimize this would actually be to combine the two P's into a single node, and maybe even combine the P, P, and Y into a single node, so that basically HA would have HA would have children S star, T star, and PPY star, if you understand what I mean. Because until we add anything else, you wouldn't have to do it. Now, if you added in happiness, then you would have to basically split off the Y, create a new node with a star, and then do the INESS star, right? And so that would only involve creating one more node rather than creating a node for each individual letter. So that's an optimization that you can do to this data structure that will save you a huge amount of node space. So let's find a dictionary. Yeah. Okay. So here's a dictionary that I have randomly found on the internet. And if you scan through it, it's just a bunch of words. So I'm going to do possibly the stupidest thing that you can possibly do. I'm going to copy paste it into Notepad++. I'm going to find replace a new line with new line add space. Let's see if this does it. It didn't like that. Oh no, oh god, it's doing. Everybody, hold on. Oh god. I might have killed it. You know, that was really stupid. I should have just loaded everything out of a file. You know what? I'm going to do that while it's doing this. Let's minimize this. We'll see if it dies or not. That was definitely my bad. Right? I mean, that's exactly what you want to do in life. You want to do a find replace on 497,000 lines. Okay. See, that was very smart. I don't know if you've ever seen the Star Trek episode with the Packlets. Not the new one with not the cartoon Star Trek Lower Decks. I mean the original Next Generation. They're like, we are not smart. Okay, so I added the file here, and how about what we do is we just add a command that loads the file. Then what we can do is we can say with open words.txt as Word file for word in Word file, which is just doing a line. We do word.strip.lower. We do mytry.insert word, word.strip.lower. And yeah, let's do it. Right, so this can't end badly. Okay, let's just add for S's and G's. Let's see what, oh look. Look what it did. It did it. It didn't actually die. It just kind of took 287,000 years to, to do that. Should I even say oops? I mean, that... Okay. So, let's insert all these words, and now let's hope. Everybody pray. Everybody hope. Get ready. Let's just say if, period... Like, let's not load in the stupid period words, because there's like a bunch of... There's a bunch of like abbreviations and crap that they put into that file. Let's not load any of those. Let's just load words. As many words as we can, right? Because if you notice at the beginning of this file, they have like all this crap here, right? In fact, why don't we just do... There we go. If it's alphanumeric, right? So if it's just letters and numbers. In fact, we can even restrict it more. There we go. Even better. Just alphabetic. Okay? Alright. So, let's do this. Sorry, data structure, you're going away now. Alright, everybody? As they say in Jurassic Park, hold on to your butts. Did it work? Oh, it didn't work. It didn't work because we needed S. Command equals load and word equals file. Okay. And now get ready for Crashville, population here. Oh, it couldn't find... Huh, it didn't do it. Is it doing it? Help me out here. What's going on? Okay, so it is loading. Alright. It is loading. Maybe is alpha is failing, so we just need to say like, so it didn't load anything. Okay, so let's give up with that and load everything. Because I'm stupid and I can't figure out... Ah, there it goes. That's what I like to see, right? I like to see it chugging along, right? Oh, yeah. So here is basically that 470,000 line list of words expressed as a data structure. Look at this thing. It's god-awful. Okay. So let's complete... let's see what happens if we complete OR. Let's look for organs... Oregon, maybe? Oh, Lord. Maybe we shouldn't be displaying this tree anymore. Because it's taking up way too much input on the Python screen. So it's... I'm sorry, print statement. You gotta go. You gotta go. Alright. Load file. And then we have to wait for it to load, because it's 500,000 words. Nice, right? Look at that. Of course, there's a lot of weird stuff in this dictionary. I mean... ornithotropy I guess I don't even know what that. I mean, I know what an ornithologist is. It must have something, right? Whatever this is, it's very strange. But here are just a ton of words that start with OR. Let's complete, say, what's a good other thing to complete? Say, rub. Rub-a-dub? Rub-dub? So yeah. Cool, right? Rubles? Rubles. So I guess, yeah. This thing is really doing its job, right? And you see how fast these searches are. Because it's able to traverse the tree. And you could even increase the speed of the search, especially if you were like, only look for words that are common or only look down paths that are common. That way you could actually, you know, you could keep track of what things are the most common paths and basically only search down those. And only if people like really try to type in, say, Rubaboo, whatever the heck that is, or Rubiot, or whatever that is. I don't even know what half of these... I think these are like slang garbage words. Like just kind of onomatopoeia words. Rubato, that's a word. That's a real word. You know... Let's find another real word here. Ruby-wise? Is that a word? Who knows, right? So, anyway. That's basically the, I think that's basically the lecture for today. You know, I think I've covered it. I think I've told you how to make one of these things. I've showed you how to do it in Python. To convert it into C++, as I say, is just a big mess because you have to, like, with a Python dictionary structure, it makes this part really, 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 really easy to handle the children. And also it means that you don't have to scan through the children to find the node you want, like if you stored this as a vector. It means that you can just jump right to the node because it's a dictionary, right? So this is like an O of 1 access time for each child. Whereas if you do this in C++ and you have a vector of nodes, and you have to do like a for, like n, you know, for like node in our children list, then this is going to be an O of n operation to search for the individual child, which you can then fix again by making, instead of vector, you make it has some hash table of, you know, node pointers, where the hash table is storing with keys, which are letters, right? So that's how to fix it, and then that's back to O of 1 time. But as I say, that's a bit more messy in C++, STL, that kind of thing. Definitely could not have... So, given the amount of time it took me to finish this, I certainly don't believe that I could have finished it in the time allotted, right? You know, I'm not a terribly slow typer. It's really just a matter of, like, the amount of code would have been, like, 4 times as much, I think. Anyway, the things that are inefficient here are really, like, string concatenations. Those are pretty inefficient. Maybe we could increase the efficiency by doing a join operation here. This is probably a pretty bad way to do this. But the good news is you don't really have to care about that, right? You're not trying to optimize this. And you also see that this thing, I mean, this thing runs relatively quickly, right? So let's... I guess happy's somewhere in here, right? There it is. Happiness. If we complete... Wow, look at that. Like, like has. And then here's hey penny. Like, ha pennies, right? For like half penny. Like the old Britishism. I don't even know what these words are. This is not hag. This is hog. This is hock. I'm not even sure, right? I think that the dictionary we downloaded is very liberal in the sense of what it counts as a word. I think if you consulted, the OED or whatever, Oxford English Dictionary or whatever it is, you would find that most of these things are in fact not in any dictionary. I just wanted to show you that you can definitely create a data structure with approximately, 400 and some thousand number nodes. Alright, so I think that's it for today. I think next time we'll try to... I might do some string matching, or we might do some graphs. I think we might do an introduction to graphs next time. Alright? So, alright, work on your projects, talk to me about stuff. Hopefully this was kind of useful. I think it's an interesting little foray into special topics data structures. So, alright, have a good rest of your day. That's all for now. Oh yeah, and if you want the code, I'll probably put it on my, GitHub.